In the last class we have discussed up to the NAND gate and NOR gate, which are the universal gates, because using those gates we can prepare even the basic gates and all possible gates that can be prepared. Now there are some questions in your mock papers to find the output and identify which type of gate this combination, certain combination produces. So see, first one is I apply only NOR gate to produce NOT gate, because all basic gates can be prepared by using NAND or NOR. So I first consider NOR gate, and using NOR gate I want to prepare a NOT gate. So that is, NOR gate is used to prepare a NOT gate. Now what NOT gate will do? Just think, this one is a NOT gate. It is a single input gate. Whenever you are supplying A, it will produce a complement. This is the working of a NOT gate. Now I am using a NOR gate. NOR gate is like this. So whenever you are giving two inputs to this NOR gate, it will produce A plus B, its complement. A plus B is OR, its complement is NOR. So that's why A plus B complement. It is produced by NOR gate. Now think of it that if I join these two channels of the NOR gate, both the channels are joined like this, then how many inputs you can give? One. And this one input is divided into two channels and fall in the NOR gate. Now what happens? There is A, there is Y. Now if you are giving 0, then on this terminal 0, on this terminal it is also 0. So 0 plus 0 will be 0. Its inversion, NOR gate will do its inversion. So it will be 1. So 0's complement will become 1. So you can prepare the truth table like this. Whenever you will put 0, Y will become 1. Okay. Because if A is 0, then both inputs will be 0, 0, 0. This will add 0 plus 0, 0. Its complement will be 1. Now if you supply 1 as A, then this terminal is also 1, this terminal is also 1. So 1 plus 1 will be 1. 1's complement will be 0. See, it is doing the same role as that of the NOT gate. So any NOR gate, when its inputs are joined as a single input, then it is considered as NOT gate. So by using NOR gate, I can prepare in this way a NOT gate. Clear? By using NOR gate, I can prepare NOT gate. Now, if it is not visible, why? These lights? No, switch on these lights. a NAND gate in a similar way. NAND gate is this one. It has two inputs, AB, and output Y will be A into B, its complement. A into B, its complement. Now, whatever AND will produce, it will produce its opposite. So, what will be what will happen if I join these two inputs together? So, there is no such B, only it will be A. So, you can write both the channels are A. This one is A, this one is also A. So, it will be A into A, its complement. Now, check. If I give A equal to 0, then 0 into 0 will be 0, its complement will be. If I get 1 into 1, 1, its complement will be 0. It is also doing as NOT gate. So, using NOR gate, you can, in this way, by joining the inputs, you can prepare NOT gate. Similarly, for NAND gate, by joining the inputs, you can prepare NOT gate. So, NAND and NOR both can be used as NOT gate by joining the inputs. Because you cannot give connect a single input to this NAND or NOT, because these are two input gates. So, you have to convert them into NOT gate, you have to join the channels and then supply the voltage. Okay. Now, using this NAND or NOT, first I will use NOR to prepare a OR gate. I will use NOR gate to prepare OR gate. See how. This one is used to prepare OR gate. Check. First we consider this one. What it will produce? If you give A and B, it will produce A plus B complement. Okay. Then divide this channel into two parts and use another NOR gate. This NOR gate will do the functioning of NOT gate. This NOR gate, second NOR gate, will do the functioning as that of this one, that is NOT gate. So it will invert the signal. Y prime will be A plus B complements complement. So it will become. So what functioning these two gates are doing? OR gate, that means addition. It is simply doing the role of a OR gate. Both used are NOR gate. First NOR gate is used normally. Second NOR gate are used like a NOT gate. So first NOR gate will produce A plus B complement. Second NOR gate is used as NOT gate. So it will invert the signal. So another complement will come and it will be A plus B's complement complement. Complements complement will be cancelled. So it will be simply A plus B. So whenever you have to prepare a OR gate using NOR gate, you have to use two NOR gates. First one is used normally, second one is used like a NOT gate. Then you can prepare that. Okay. Now, so here I show that this one is the presentation of a NAND gate is used to produce NOT. Here NOR gate is only used to produce OR. Now I will check how using NAND I can produce AND. Same thing, dual channel. First one is normal NAND. What it will produce? Y. It will be A into B's complement. Then use another NAND like a NOT. So it will produce Y bar, that is A plus into B's complement. It will become A into B. So NAND is producing AND. Similar method. First one is normal NAND gate, second one is NAND gate used as NOT. You can produce AND gate. Okay. Now we have to produce using NOR gate, we have to prepare AND gate, and using NAND gate we have to prepare OR gate. See how. This one, one NAND gate, and there is a signal E. NOR gate. NOR gate is used in as a NOT gate. NOR gate is used as NOT gate for signal A. Similarly, I will use another NOR gate as this one for signal B. What they will produce at the output? A complement and B complement. They will produce at the output. Now, these two outputs are again passes through one OR gate used normally. So what this NOR gate will do? This will add the signal A complement plus B complement, and they are producing whole complement, A complement plus B complement, and its inversion, because that is a NOR gate. So it will do the functioning of OR and then invert like NOT. Clear? Now A complement's complement, A complement plus B complement whole complement. Just identify the De Morgan's law. What it says? A plus B complement will become A complement into B complement. A plus B's complement equal to A complement plus B complement. You have written this one is De Morgan's first law. Now use this De Morgan's law. This will be then not A and B, there is A complement and B complement. So it will be A complement complement into B complement complement, which is nothing but A into B, means it is doing the operation of a AND gate. So 3 NOR gate together can produce a AND gate. Three NOR gate together produce AND gate for its verification. That is A complement plus B complement whole complement. That will become A complement complement into B complement complement. Complement's complement is the original function, that is A into B. Here NOR gate is used to produce AND. Now we will produce OR gate by using NAND. In a similar method, dual channel, take AND. A is given, dual channel, another AND, B is given. It will produce A complement, it will produce B complement. Okay, because here AND is used as NOT, so producing the complement only. Then these two are passing through in an AND gate, NAND gate normally. So what this will do? NAND gate means multiply the two signals and then take its complement, because it is NAND. So this output will become A complement into B complement, its whole complement. Because NAND gate will multiply the two inputs, one input is A complement, another input is B complement. So NAND gate first multiply both and then take its complement. Then use De Morgan's second law. Second law is A into B complement equal to A complement plus B complement. Now here there is not A, there is A complement, so it will come A complement complement plus B complement complement. Complement complement will be original function, A plus B. So it is doing the role of a OR gate. Okay, now there is a easy way to remember how many gates to use to prepare what, how many NOR gates or how many AND gates are used to prepare NOR gate, OR gate or AND gate. See, the name, follow this name, NOR, which is there. So to prepare OR, you require two gates, two NOR gates. Check. Using NOR, when we prepare OR, we require two. And name of the AND gate is not in NOR. So to prepare AND, you require 3. So if the name is included, then you require 2 gates to prepare that. So NOR gate includes the name of the OR gate. So when using NOR gate, you try to prepare OR gate, you have to take 2 NOR gate. But AND name is not included here. So to prepare AND, you require 1 more. Same thing goes with the NAND gate. AND is there. So to prepare AND gate, 2 NAND gate is used. And using NAND, when you try to prepare OR name is not included here. So 3 NAND gates are required. So you can remember in this way that if the name is included in that, then to produce that, I have to take 2. If the name is not included there, I have to take 3. Okay. Now one more get that we will discuss, that is called exclusive OR gate. Exclusive OR gate or XOR gate, short form. These are the two channels, A and B. Now from these two channels I prepare this kind of a setup. There is a NOT gate which is producing A complement. There is another NOT gate which is producing B complement. Okay, two NOT gate is used, one with channel A to produce A complement, one with channel B to produce B complement. Then take these two, and pass them through an AND gate. What this AND gate will produce in the output? A complement into B, that is producing A complement into B. Okay, A complement is there, this channel is B, so it is multiplying this to A complement into B. Then take this one here and pass it through another, join it to another AND gate. Its output will become A into B complement, because its first channel is A, second channel is B complement, so it is producing A into B complement. Now pass these two inputs, two outputs at the input channels of an OR gate. What output it will produce? A B complement plus A complement into B. A B complement plus A complement into B. This output is called the output of a exclusive OR gate. Exclusive OR gate. First we prepare the truth table. A, B, A complement, B complement, Y. Prepare this truth table. 0, 0, 1, 0, 0, 1, 1, 1. Okay? Now, 0's complement will be 1. So, 1, 0, 1, 0. 1, 1, 0, 0. Now calculate Y carefully. A B complement. A into B complement, or better to draw two more steps then come to Y. Otherwise there is a chance of writing wrong. Then write Y. Then it will be more better. Calculate first one. A B complement product 0 into 1 0 1 1 0 0 1 0. Verify. A B complement 0 1 0 1 into 1 1 0 into 0 0 1 into 0 0. Okay. Now we have to calculate A complement into B. What is A complement? This one. B is this one. So 1 into 0. 1 into 0 is 0. Then 0 into 0 0. 1 into 1 1. 0 into 1 0. Then add. It will be 0, it will be 1, it will be 1, it will be 0. Now verify with this two and the final. If both the inputs are 0, output is 0. If both the input is 1, output is 0. If the inputs are not equal, then output will be 1. Inputs equal, it may be 0, it may be high voltage, it may be 1, output will become 0. So input should not match. If the input matches, output will be 0. Whether inputs are 0 or whether inputs are high voltage, that doesn't matter. It will be immediately 0. And input are mismatched, then in the output it will show 1, high voltage. That is called exclusive OR gate. It is written, it is entire circuit symbol of this one is like this. There is an OR gate. This much we have to discuss in logic gates, and now we will discuss the other topics. Okay, I think now you can solve the problems of the logic gates, because this one is actually a very easy topic compared to the other topics of mechanics, rigid body mechanics and all these things. This topic is comparatively easy. Now we will discuss a topic of thermodynamics, because this topic is common to chemistry and physics both. But in the physics we require only the basic parts. In the chemistry you will learn it in detail, because enthalpy calculation, Gibbs free energy calculation, all these things are in chemistry. It is chemical thermodynamics part. We will only discuss the basics parts of the thermodynamics that is related to physics. Okay. First of all, before studying thermodynamics, you have already studied one chapter related to the motion of large number of particles, mainly to the gas particles, that is kinetic theory of gas. And before that we have studied for particle motion the Newton's laws of motion, right? Now consider in this room, let us consider this one is a closed room. How many gas molecules are present in this closed room? Infinite number of gas molecules are present in this closed room. Okay, fine. Let us consider a small water bottle. Okay, completely evacuate the water from it, and very small amount of gas is there. Suppose this bottle, entire volume of the bottle is filled with certain gas. Okay, how many number of gas particles are there? Even close to infinite numbers. Because if, okay fine, I consider 1 mole of gas only, it contains 6.022 into 10 to the power 23 number of molecules, and even this can be considered as infinite number of molecules. Then consider, if I want to discuss the motion of these gas molecules, can we apply Newton's law to calculate the external force on each and every gas particles and then calculate the acceleration and summed over it? It's not possible. 2-3 generations will pass away, but still you cannot calculate. That's why scientific community did a very tricky job. They consider a single gas molecule, calculate the force on the gas molecule, and predict all the gas molecules will feel the same amount of force. Can it be done? Can it be done? Suppose I consider Rakibul and say what Rakibul studies every day, everyone studies that much of amount every day. It's an overestimation. It may happen that someone is studying more than Rakibul, someone is studying less than Rakibul, someone may study equal to the Rakibul that's studied in one day. So you are doing some overestimation in that process. But gas molecules is not like Rakibul. That is very tiny particles and they are almost having almost same force when put in certain container. So we can do that. But still overestimation. That method of calculating the force on one particle and generalize to say that every particle will experience the same amount of force, and we can do all the calculation by considering that. That method is done in kinetic theory of gas. Okay, so kinetic theory uses this technique. That's why in kinetic theory you are overestimating something. Now this approach is going to the molecular level because you find each and every molecule calculate force. One molecule may, someone can take, okay fine, I will take 10 molecules, I will take 100 molecules, I will not make that overestimation of on one molecule only. Okay, but if someone take 100 molecules, that does not matter anything because 6.022 into 10 to the power 23 is a very large number. Clear? Now, this method is the microscopic view to the gaseous system. But most of the people at that time are raising questions that why this overestimation is done. Because we cannot go into the entire detail of each molecule, then what is the utility of this process? So that's why there are other scientific communities which they are trying to find out on a macroscopic level what is doing with the gaseous system. We want to study the motion of the gaseous system from a macroscopic level. Macroscopic level means we will not discuss what will happen to the microscopic level. Clear? Now, you are saying that okay, I will forget everything about the microscopic level and only take the macroscopic level. Now suppose this program, star 30 program, if it happens that most of the students of all of you get a chance in the NEET exam, let us consider all of you get a proper chance in the NEET exam. Does it mean that you are not studying anything and you get chance in the NEET exam? No. You study everything, you have do a study, fine, then you can only get a chance in the NEET exam, because macroscopic level of the success of this program is actually coming because at the microscopic level you are working properly, sincerely, right? So macroscopic levels result cannot ignore the microscopic levels preparation, right? So same thing happens with the gas molecules. What gas molecules will feel at the microscopic level, each and every atom feels certain amount of force, then only in the macroscopic level you can get proper pressure, proper volume and proper temperature of the gas. Means none of these macroscopic variables are not related to the microscopic level. They are solely related to this microscopic behavior of the gas. That's why thermodynamics is an exact science and it produces the result almost correctly in every phenomena. Clear? The concept, is there any doubt you can ask? Fine? Now microscope, as a macroscopic variable I mentioned 3 variables: pressure, volume and temperature. There are other macroscopic variables in thermodynamics you have already studied. Internal energy, total amount of heat, and in chemistry you have studied enthalpy, entropy, all these things. Then why this particular P, V and T are taken? Why particular P, V and T are taken? Why not the others? See, these 3 we can directly find their relationship with the microscopic details. First variable, pressure. With which microscopic phenomena pressure is related? Gas molecules are moving and they are colliding with walls of the container, and that creates the change of momentum of the gas molecules, because this gas molecules collisions with the wall is considered as perfectly elastic collision. So gas molecules rebound from the wall and there is a certain change in momentum, and that change in momentum produces impulse. Impulse means change in momentum per unit time, that is related to force. Force per unit area is pressure. So if more and more number of molecules are striking with the wall, then more and more change in momentum will occur and that generates more pressure. So number of collision of gas molecules with the wall is a thing that is responsible for pressure. So write down, pressure of a gas is related to the microscopic phenomenon of collision of molecules, collision of gas molecules, microscopic phenomenon of collision of gas molecules to the container wall. Okay, so how much collision is occurring at the microscopic level, that is actually determining pressure. Though we measure pressure as a macroscopic quantity, but it is highly related to this microscopic collisions. Now the second quantity that we discussed, volume, how it is related to the microscopic results. Okay, in case of real gases, we consider that there is no intermolecular attraction force between the real gas. But can this type of gas occur in reality? No. So the real gases, in case of ideal gas, we consider there is no intermolecular attraction. But normally the gas that we found are not ideal gas, they are real gas. For real gas, there is a very small amount of attraction force between the gas molecules, and as a result the gas molecules are not going freely from each other. That determines the volume of the gas, because if the molecular gap force is weak, then molecule can go far away from each other and volume occupied by the gas will be more. So intermolecular force is directly related to the determination of the volume occupied by the gas. So if intermolecular forces will change, the volume will be affected. Okay, so write down volume of the gas is related to the intermolecular space. Volume of the gas is directed to the intermolecular space, which is related to intermolecular attraction, which is related to intermolecular attraction. Volume of the gas is related to intermolecular space, which is related to intermolecular attraction. Now, temperature. How it is related? It is the average kinetic energy of the gas molecules. That is called temperature. Means how fast gas molecules are moving. On its basis, its temperature is dependent. Because if in a container certain amount of gas is there and you are heating this gas, as a result its temperature will increase, means random motion of its molecule will increase. Previously they are moving in random motion, but like this. Now as the temperature is, their speed will increase and motion will be too much random. So temperature of a gas is related to the average kinetic energy of the gas molecules. So that is also a macroscopic phenomena of randomness. Randomness in motion of the molecule means more temperature. More randomness, more temperature. Okay. Repeat. Write down. Temperature is related to the average kinetic energy of the gas molecules. Temperature of a gas is related to the average kinetic energy of the gas molecules. Now, with this P, V and T, we can enter into thermodynamics. What I have said, that how P, V and T are related to all these things, and why P, V, T, these are regarded as the thermodynamic coordinates, all these things are mainly mathematical phenomena to describe a molecule, a gaseous system or a very large number of system, bulk matters. But how the thermodynamics was discovered? Not in this following path. This is the mathematical development of the thermodynamics that was realized later. But at the initial level, when experimentalists developed thermodynamics, they completely come from a different perspective. You may find two concepts here and there. One is, write down, heat. Mechanical work, internal energy. Heat, mechanical work, internal energy. To say what is the difference between all these three quantities? How can you distinguish? what is heat, what is mechanical work, what is internal energy. Most of the things, these three quantities are related by first law of thermodynamics. So what are the difference between all these three? Internal energy, heat and mechanical work. See, first of all, tell me what is heat? What is heat? You know it very well. Yes? Measure of hotness and coldness. Okay, fine. This can be one definition of heat, but not very intuitive, not very informative or related to the thermodynamics. It is just about the feeling, but it is related to someone's feeling. Measure of hotness or coldness. Someone can stand up to 100 degrees Celsius. Someone say, oh, 50 degrees Celsius is very hot. Then someone of you say it is a form of energy. Like when I asked someone what is light, someone is saying that it is a form of energy. I say, okay, the observer is a blind person. Okay, so heat is form of energy, true, but then how to distinguish it from other form of energy like internal energy that you have mentioned? Then someone say, okay, internal energy is form of internal energy, heat is also a form of internal energy, so both are same. Write down one statement. A body of certain mass contains an amount of heat 50 calorie, contains an amount of heat 50 calorie. What does it mean? What does it mean? Someone say you a body of a certain mass contains this amount of heat, certain amount of heat, 50 calorie. What does it mean? Body contains heat 50 calorie. What does it mean? No. This means nothing. The statement is wrong. Because when the energy is contained in a body, it is not called heat. Heat cannot be contained in a body, by a body. Heat is the energy in transit from one body to another body. When energy in transit, that is called heat. When the energy is contained in the body, it is called internal energy. So that is the difference. Entire thing is energy. When it is inside the body, it is called internal energy. When it is transiting from one body to another body, during the transit process, this is called heat. Okay. And when it is again absorbed by the other body, it is converted to the internal energy. Only during the process of transfer, it is called heat. So that's why when most of the students write heat contained by a body, this is a wrong statement. Heat cannot be contained by a body. It is contained by, energy is contained by a body, not in the form of heat, it is in the form of internal energy. Write it. When energy is contained by a body, when energy is contained by a body, it is called internal energy. It is called internal energy. When the energy in transit from a body, when energy in transit from one body to another body, it is called heat. It is called heat. Now, for this transiting of heat, how many processes normally we can consider? Generally, see, if there is a temperature difference, then heat can flow from one body to another body. Energy can flow from one body to another body in the form of heat. That is called sensible heat, that we can sense. Another is during change of state, that is called latent heat. Two procedures of them. So sometimes when we call, suppose a ice block is there, it is absorbing a latent heat and then melts to the water. Absorbing heat is coming to it, to the ice block, then it is heat. After absorption, it will be converted to internal energy. So internal energy increases, and as a result it will melt. It will melt to the water. Internal energy increases, but now you can say that internal energy increases means temperature will increase, but during the change of state temperature will not increase. Not only internal energy will increase, in this process temperature will not increase due to internal energy increase. What changes? The intermolecular force is weak, and as a result it will not be in the solid structure, it will melt to the liquid structure, because in liquid structure, in water molecules, the intermolecular attraction is less than the intermolecular attraction of the solid form. So whenever in the solid form, internal molecular force will be stronger. When it is in the liquid form, internal forces is weak. When it is in the gaseous form, it is further weak. Clear? Now, how these things are discovered? There was a scientist called Count Rumford. Count Rumford. Before Count Rumford, there is a consideration that heat is like a fluid. Invisible fluid is colorless, odorless fluid. You cannot see it, and that is named as caloric. When caloric, this fluid, enters into a body, it will become hotter, and the body which loses caloric will become colder. This type of theory is there. One day Count Rumford was drilling in a iron plate, iron sheet. He was drilling with a drilling machine, and he found that this iron sheet and the drilling needle, all these things are too much hotter, became hotter. Then Count Rumford started to think that how caloric will enter in this material to get it hotter. So he touched here and there all the objects in the room to find that which one will become too cold, but he can't find any object in the room which are so cold that he can predict that caloric from that body enters to this one. Okay. Now Count Rumford, to make sure that how caloric is coming, he is doing this experiment by putting this metallic iron disc inside ice cold water, the water at 0 degree Celsius. Some ice is dropped in the water and then the metallic disc is inside water, immersed inside water, and now by the needle he start the drilling. And as soon as the drilling starts, Count Rumford noticed that the temperature of the water is increasing, and even the ice cubes which are floating, this starts to melt. So at the end of the result, Count Rumford find that temperature of the water increased by an appreciable amount and all the ice cubes are melt. Now Count Rumford is in tension. That is, entire water is there. If this metallic plate is getting hotter, means from the adjacent water caloric must go inside that, means adjacent water must become more cool. But on the other hand, adjacent water becomes hot. So then Count Rumford declares that there is no such invisible fluid like caloric which enters from the other body and comes from the other body and enters into this. It is the process of drilling that produces mechanical work done. Process of drilling means friction is there, and as a result there is some mechanical work, and this mechanical work is converted to internal energy, and as a result temperature increases, and this internal energy also flows from the metallic disc to the water. As a result, temperature of the water will also heat and heat into mechanical work. Then this interconversion is possible, and the relation between interconversion of heat to mechanical work and mechanical work to heat, that is the fundamental calculations of thermodynamics. So that's why we read thermodynamics, to find the relationship how mechanical work can be converted to heat, and then heat can be converted to mechanical work. How efficiently we can do these processes. That is related to the first law of thermodynamics and related to the other second law. Then there are other implications of the second applications of the second law. We will not discuss that. Mainly we are concerned with this, how what is the relation between mechanical work and heat energy. Clear? The goal of thermodynamics. Now, as we discussed, there are three variables: pressure, volume and temperature. Volume, temperature. These are called thermodynamic coordinates. Thermodynamic coordinates. Thermodynamic coordinates. Pressure, volume, temperature. Okay. Now, coordinate you have already found in mechanics, that is x, y, z, Cartesian coordinate, where x, y, z all axes are perpendicular to each other and they are called mutually independent coordinate. Perpendicular to each other means they are mutually independent. Now, are these thermodynamic coordinates mutually independent like the coordinates of mechanics? No. There are relationship between these thermodynamic coordinates P, V and T. Suppose I assume a empirical relation, that is function of pressure, volume, temperature, that will be 0. Any kind of equation. with P, V and T that can be written, I write the general form and empirical form, function of PVT equal to 0. Okay. Now, can you write this type of a relation in any situation? Only in case of an equilibrium state. Now already the question comes, what is equilibrium state? Equilibrium state. Write it. This type of equation can be written in a state. This type of equation can be written in a state which is in thermodynamic equilibrium. Thermodynamic equilibrium. Thermodynamic equilibrium. See, there are two different logics. One is thermal equilibrium, another is thermodynamic equilibrium. So first we consider the thermal equilibrium. Okay, so write down thermal equilibrium. Thermal equilibrium means there will be no, if two bodies are in thermal equilibrium, body 1, body 2, there will be no exchange of energy between them in the form of heat. Heat exchange is strictly prohibited if the bodies are in thermodynamic equilibrium. Clear? Means they are at the same temperature. So if there is no exchange of heat, we can consider they are at thermodynamic equilibrium, means they have the same one property same, and that is same temperature. Clear? You know the name of this law from which it comes. 0th law of thermodynamics, because second law and first law are discovered earlier, and after that people realize that thermodynamic equilibrium is required, so they put it as 0th law, which says that if two bodies are in thermal equilibrium, suppose A and B are in thermal equilibrium, A and C are in thermal equilibrium, then we can say that B and C are also in thermal equilibrium. Thermal equilibrium is ensured only by same temperature. Okay, so that is coming from the 0th law. So write it. Thermal equilibrium means we are discussing about a system, thermodynamic system. So thermal equilibrium means every part of the system has same temperature. Okay. Suppose this is the thermodynamic system, this water, means every part of the water has the same temperature. There is no temperature difference between every part of this water. Any part of this water, there is no temperature difference. Now, if I ask you, the sea water, is it in thermal equilibrium? No. Some water, due to water current, some portion is hot water, due to some portion is cold water. So they are not in thermal equilibrium. Now second one, right? Mechanical equilibrium. Mechanical equilibrium. Means there should not be any force, any net force. There should not be any net force acting on any part of the system. There should not be any net force acting on any part of the system. So in that case we can consider it is in mechanical equilibrium. Third one, chemical equilibrium. Chemical equilibrium. There should not be any unbalanced chemical reaction. There should not be any unbalanced chemical reaction acting at any parts of the system. Any parts of the system. Okay. Suppose in water, if I drop certain amount of calcium oxide, chemical reaction starts, heat will be produced and it is no more in equilibrium. Equilibrium is destroyed. So when all these three equilibriums occur together, then it is called thermodynamic equilibrium. So thermal equilibrium is only a part of thermodynamic equilibrium. Thermodynamic equilibrium is a global idea. That means thermal equilibrium, chemical equilibrium, mechanical equilibrium occurring together. Then only you can write this type of equation between P, V and T. Not always. But we forget for work. When we are solving problem, we write always. Okay. Now, it is showing that function of PVT will be 0. Means I can write some T as some function of P and V. T can be written as some function of P and V. Suppose this kind of a relation, say P square minus V T equal to 0. The empirical form of any relationship like this can be written like this. Then from this, can I write T equal to P square by V? It is possible. So that's why I write from this, I can always write T as a function of P comma V. But it can be a different function. So that's why I write F1. Okay, fine. Then I can also write, say that I can write P equal to some function of V and T. Check. From that I can also write P as root over of Vt. Different format function, so I write F2. I can also write V as some function of P and T. V can be written as P square by T, so I can write. Now once the system is taken, is its mass variable or is its mass constant? Constant. I am taking a particular system, suppose this glass water, so its mass will become constant. So we have already considered that mass of the system m is constant. Okay. Now, if mass is constant and consider for that system, and we consider it is an ideal gas. If you consider T is constant, then function of P and V are variable. Then for every P and V, T will become a constant, mass is also constant. So you are getting a relationship between pressure and, that is your Boyle's law. This relationship leads to the Boyle's law. Mass constant, temperature constant. This one leads to pressure constant, mass constant. Relation between V and capital T means Kelvin scale. That is Charles' law. Remember, it is in Kelvin scale, so it starts from 0. In Celsius scale, it starts from minus 273. And next one is the Gay-Lussac's law of pressure. So in this case, mass constant, pressure constant, and in this case, mass constant, volume constant. So all are coming from the same empirical relation, function of PVT equal to 0. 3D. Each of the variables, since they are not independent, you can write any of them in the form of other two. And if you put that variable function to be constant, T is constant, then we get Boyle's law. P is constant, we will get Charles' law. V is constant, we get Gay-Lussac's pressure law. Okay. Then what this function of PVT equal to 0 represents? This is giving a relationship between PV and T from which all this can be derived. Then that particular is PV equal to nRT, that is the equation of state from which everything can be derived. See, T constant means this part is constant. So P proportional to 1 by V. PV constant means P proportional to 1 by V. Boyle's law. Now, if P constant, V proportional to T, Charles' law. If V constant, P proportional to T, Gay-Lussac's law. So that empirical form which will contain all the three individual laws is called the equation of state. The name, see, equation of state. Which state? Equilibrium state. Which type of equilibrium? Thermodynamic equilibrium. So that's why it is termed as equation of state. For anything you cannot write. If it is not an equilibrium state, you cannot write this law. Now from this we have to define certain things and then we can directly go to the first law of thermodynamics. See, certain things we have to discuss. One is system, second one is boundary, third one is process. System, surrounding, process. But before that I have to discuss something else. What do we mean? First say what is system. System means anything of the environment that we can choose to discuss. Suppose this water, that is my system. Now how many types of system can be? There are three types of system. Open system, closed system, isolated system. Open, closed, isolated. What do we mean by that? This one is a system. System. Anything outside that which can affect the system is called surrounding. Anything outside that can affect the system. Suppose here is 1 cup of tea, hot, 1 cup of hot tea. Now this fan is directing towards this cup of tea, so its temperature will decrease. So this entire room's air and this fan blowing is actually affecting this one. So I will consider this one as the surrounding of this cup of tea. Cup of tea is considered as the system. Now you are saying that, okay sir, there is cup of tea and in kitchen someone is switching on the oven, so your cup of tea will become more and more hotter. That is not possible. That is not your surrounding. Surrounding have to affect this one. Okay. Then this is system, this is surrounding. System and surrounding together called thermodynamic universe, not the entire universe. It is the thermodynamic universe. System plus surrounding is called thermodynamic universe. Thermodynamic universe. Now, I said 3 types of a system. First one, second one, third one. Open system, closed system, isolated system. Open system means mass and energy both can be exchanged between system and surrounding. Mass and energy both can be exchanged between system and surrounding. Then it is called open system. Okay. Next. If only energy can be exchanged between system and surroundings, flow of mass is prohibited. Then it is called closed system. Only energy can be exchanged, mass cannot be exchanged. Then it is closed system. Nothing can be exchanged, neither mass nor energy. Then it is isolated system. Neither mass nor energy, then it is isolated system. Okay. Now in thermodynamics, what we will discuss, as of now we will discuss only for closed system. Mass cannot be exchanged and only energy can be exchanged, not even the isolated system, only the closed system we will discuss. That is only in the syllabus, some part of it. Now come to the boundaries. System is separated from the surrounding by this thing called boundary or a wall. Boundary or wall. This wall can allow heat to exchange this wall can not allow, sometimes this wall will not allow heat to be exchanged. If the wall is allowing heat, then this type of wall is called diathermic wall. Diathermic wall. If it is not allowing heat energy, then it is called adiabatic wall. Okay, so write down walls allowing heat exchange. Wall allowing heat exchange is called diathermic wall. Diathermic wall. And not allowing heat exchange is called adiabatic wall. Now, how many processes you learned in thermodynamics? Ideal processes? 4 ideal processes, that is isothermal process, adiabatic process, isocodic process, isobaric process. Okay. Now, every process should be infinitesimally slow. There should not be any very fast process. That's why all processes in thermodynamics are quasi-static process. Quasi-static. Now what do we mean? Suppose because unless you write equation of state, you cannot proceed for calculation of thermodynamics. Because for every state you have to write PV equal to nRT. If you can't write this equation, you cannot proceed to thermodynamics. See, why quasi-static process is required? Let us consider there is certain gas in a piston. I consider as of now ideal gas, and there is some piston fitted in this container. This is a cylindrical container. Inside the container there is certain amount of gas. Okay, certain amount of gas is there inside the container, and this is a cylindrical container, and this is completely an airtight movable piston attached to this end. Airtight movable piston. Now at this moment, suppose it is the initial state defined by pressure P1, volume V1 and temperature T1 at this moment. Initial state. I can write here that this relation is obeyed. P1 V1 equal to nRT1. Equation of state. Now you have to, in thermodynamics, you have to change the state to other, and then due to that change, heat energy absorbed, work done, internal energy change, that we have to measure. Okay. All this we have to measure in thermodynamics. In first law, you know. So suppose I have to change that state, and there is some thing. I put a 10 kg mass over this, 10 kg directly. What will happen? The piston will come down abruptly, momentarily. It just comes to this point, suppose, compressing the gas very quickly. And now you are saying that I will remove this 10 kg mass. What will happen? It will jump up. Up to which height? Up to the previous height. Are you sure it will come to the previous height or not? Why not? Because all steps are reversible. That is not sure. What you have done, you have put 10 kg like an impulsive force, like this. Now when you are releasing this one, you are saying that okay, fine, this will go through all the same steps and come back to same thing. I can show you this one with one example. Come, see. Him, I am applying a force on him. Okay? Now I am releasing this force slowly. Is there any change in shape? No. Okay, fine. Now I am saying that okay, I will release this force, he will come to the same shape. Is it true? It may happen that his bones can break, all these things. Means whenever you put this 10 kg, so much impulsive force is given. Going in a rush, compress the gas quickly. It may change the internal energy, and as a result temperature can be changed, increased. And when you release so fast, it will cool down. But in this abrupt process, each and every step when going down and each and every step when coming up are equal, you cannot see. So that's why it is not a reversible process, it is completely an irreversible process. And in this case, you cannot apply this equation of state for all states. Okay, then what we can do? We can do in very small steps. How much smaller? Suppose 1 kg at a time. But still 1 kg is very large. Okay, 500 gram. That is very large. 1 gram. Someone is saying that is also very large. So take it 1 milligram. By 1 milligram, 1 milligram, 1 milligram, you have to go to the 10 kg. Means how much time is required? Very large time. And as a result, we are in a process to describe the different processes. First one is isothermal. Then is adiabatic. Then isochoric. Then isobaric. Then isothermal process means temperature will not change, means dT will be 0. Adiabatic means no heat energy exchange between system and surrounding, that is dQ equal to 0. Q is determining the heat energy. Isochoric means volume remain constant. Isobaric means pressure remain constant, so dP equal to 0. Okay. Isothermal, dT equal to 0, adiabatic, dQ equal to 0, isochoric, dV equal to 0, isobaric, dP equal to 0. Okay. Now, I will write certain more things for some processes that we will discuss during the study of the first law. In this process, you can also write dU equal to 0. Means in isothermal process, internal energy of an ideal gas will not change. This one is called, can be written like this, called isentropic process, means entropy of the gas will not change. Entropy of the gas will not change. That is called isentropic process. Okay, adiabatic and isentropic, same. dV equal to 0 means work done by the gas will be 0. Gas is not doing any work. Isobaric means dP is 0, there is no other thing. So only these three processes we write different also. This can be denoted by du is 0, ds 0 and dw 0. Now, we will come to certain properties of the thermodynamic functions like total energy, heat energy, internal energy, work done, and all these things. You will find two types of name. One is called the state function, another is called the path function. State function, and path function. State function, path function. State function depends on only endpoints. That means at the beginning of the state and at the end of the state. And path function is not that. Path function is depending on each and every point through which the system is going. That is called the path function. Now, suppose you are going from this Shillong to Kolkata. How many processes you can follow? Many. 2 processes, 3 processes you can follow. Suppose you can go to Guwahati and then take train. You can go to Shillong airport. You can avail plane. You can go to Guwahati airport and from that you can avail plane. Someone can say that okay, I will go to Guwahati, from Guwahati I will go to Shiliguri by bus and then by bus I will go to Kolkata. And even someone can say I am like any monk and I will start walking and one day I will reach Kolkata. Okay. Many processes are there. But what is your starting point? Shillong. And after all, at the end point is Kolkata. So, the starting and end result, these are fixed. So, any kind of function which is depending only on starting and ending, that is called the state function. Starting and ending is fixed. Any point through which it can go, that doesn't matter. Suppose in the Shillong, you are starting with nothing in your pocket and after reaching Kolkata, you are given 1000 rupees. So, in whatever be the process, you will reach Kolkata, you will get 1000 rupees. So, starting and ending result is fixed. What is happening here? That doesn't matter. But see now, the energy that you spend, the tiredness that you are feeling in this, all these processes are different. So that is a depending on the particular path chosen by you, that is a path function. Clear? Now in thermodynamics, how these are utilized, 3 quantities we are dealing with: internal energy, heat and work done. Among these 2, work done and heat are the path function. They depends on the particular path followed. And internal energy is not a path function. It depends on the particular initial and final point only. So internal energy is called a state function and heat and work done is called a path function, right? Heat and work done are path function, internal energy is a state function. Now why? See, if the internal energy of the body increases, then its temperature will increase. Now think about it. I want to increase the internal energy of this 2 pound. Okay. How can we do that? That is by doing mechanical work. I can increase the temperature. That means there is an increase in internal energy. Other thing is that I can put both of the pump near a oven. In that case, there will be temperature increase of my hand. Okay. So both the processes are actually increasing the temperature. Suppose by same amount 10 degrees Celsius. Now you said someone, okay, I increase my temperature of my pump by 10 degrees Celsius. Can he tell, if he is not observing to the processes, can he tell by which method you increase the temperature? By rubbing or by putting it near the oven? You cannot say. So only he can, by thermometer only he can say that initial point, suppose their temperature is 30 degree. Now again after some time he put the thermometer and find the reading to be 40 degree. So he will say, okay, fine, temperature of your hand is increased by 10 degrees Celsius. But I don't know how you increase this temperature, by doing mechanical work or by taking heat energy. So heat energy and mechanical work, these are different processes which are following path. But the increase in internal energy is only depends on the initial and final position, not on the particular path. So internal energy is state function, where heat and work done both are path function. Clear? Is it clear to everyone? Now we are considering a process. Suppose from process 1 you start suppose from A you start and you reach to the final point. So let us consider it is initial point I, this is final point. This one is process 1, this one is process 2. Now at this point, if you are going to this one, so you are following a particular path, so there is a change in internal energy. Now you are following other path to come back to this process. This type of process completes a cycle, means initial point and final point will actually coincide after 1 and 2, both the cases. I to F, then F to I. This is called a cyclic process. Now internal energy depend on only initial and final state. Now see, after coming back here, initial and final state will be same. So change in internal energy in any cyclic process will be 0. 0, because it starts from this state, goes there and come back. Since internal energy is a state function, it only depends on initial and final state. If initial and final state coincides, then change in internal energy will be 0. Change in internal energy 0 means this process is, this one is cyclic process. Now, so we can say that for any cyclic process, change in internal energy will be 0. Because internal energy is a state function. Because initial and final state coincides in cyclic process, so internal energy comes to be 0. Now, if there are any other state function and it is following a cyclic process, then for all those state functions, after the cyclic process, change in that variable will become 0. Not only internal energy. Internal energy is just an example of a state function. There are many state functions you will occur in thermodynamics. Entropy is also a state function. Okay, but for path functions that is not true. Work done in path 1 from I to F and work done in path 2 are not numerically equal. So you cannot say that entire work done after the cyclic process will become 0 or entire heat absorbed by the gas in the cyclic process is 0. You cannot say. Clear? Now come to the first law of thermodynamics. I consider there in that example of increasing the temperature of my pump, I consider that internal energy is increased by how many methods? Two methods. One is by giving heat energy, other is by doing mechanical work. So let us consider, instead of my hand, this is a thermodynamic system. So its internal energy can be increased by an amount, say du. Now this can be done in two processes, one by supplying mechanical work, another by supplying heat energy. So by supplying heat energy and doing mechanical work. Now who is doing this mechanical work? You are doing this mechanical work. So that is considered as positive. If the system is doing mechanical work, that is considered as negative. If external agent, I am doing the mechanical work and I consider it is positive. Then if I consider this is done by the system itself, then it is considered as negative. So now we consider everything from the perspective of the system. So if system is doing mechanical work, instead of this dW, I will write minus dW. Then immediately you can write this expression as dQ equal to du plus dW. Okay, dQ equal to du plus dW. Now you can, both of these are the form of first law of thermodynamics. First I consider in the form of the state function and path function. Now I consider this law in the form of conservation of energy. See how. Suppose there is a system, suppose a gaseous system, a gas balloon. You are supplying certain amount of heat energy to this gas balloon. What will happen? The temperature of the gas inside the balloon will increase, means there is an increasing internal energy of the system. Moreover, the balloon expands. If you are putting heat energy, then gas will expand, means the volume will expand. So the balloon will expand. Expansion means molecules are moving. So it is doing mechanical work. That can be calculated by this dW, which is can be written as du plus pdv, means dW, can you know this formula, dW equal to f dx, force into displacement is work done. Then if I consider the area of the substance is A, the area of this balloon is A, then we can write F by A into A dx. F by A means pressure and A dx is change in length, that is determined by change in volume. So that is PdV. So that's why I write dW equal to PdV. Now you can say that if I supply certain amount of heat energy dQ to a gas, gas will utilize this heat energy into two parts. One part is utilized to increase its temperature, means increasing its internal energy. Other part is utilized to do some mechanical work. The system will expand and do some mechanical work. So this is the conservation of energy, nothing but total energy supplied, it is utilized into two parts. So sum of those two parts equal to total energy, that is just a conservation of energy. So you can think of that this first law of thermodynamics is just a conservation of energy. from this we can define certain processes and we can do something. First one is from this we can calculate the difference of two specific heat of gas, difference of some other the different calculation of the work done in any process, that all those things that we can derive from here. Now, first thing that we are going to discuss, first to define the specific heat capacities. Specific heat capacities. Now, what is specific heat capacity of any substance? Normally we say that for copper specific heat capacity is 0.09 calorie per gram per degree Celsius, means 0.09 calorie gram inverse degree Celsius in inverse. Means if you have a copper block of mass 1 gram, then to increase the temperature of this block by 1 degree Celsius, you have to supply 0.09 calorie of heat energy to this block. Okay, so it will absorb this amount of energy, this amount of heat, 0.09 calorie, then its temperature will be increased by 1 degree Celsius. That is called the specific heat capacity. Now, for the gas, if I consider a certain amount of gas, its mass is say 1 gram, you have to supply certain amount of heat energy to it to increase its temperature by 1 degree Celsius, then that is called the specific heat capacity for the gas. Now I ask you, when you write this one for copper, what you are doing? Copper chunk is there, 1 gram mass, you are supplying heat energy until its temperature increases by 1 degree Celsius. Achha, in this process, what you kept constant is the pressure kept constant or volume of the mass kept constant. Have you noticed this one? When you write this one, have you noticed that this heat energy is supplied? Okay, fine. But during that process of supplying heat energy, whether mass is volume is remain constant of the copper block or the pressure on the copper block remain constant, that you completely ignore. You can ignore it for copper because it's a solid. But in case of a gas, you cannot ignore it, because if you calculate the required energy for rising temperature by 1 degree Celsius for 1 gram of gas, then in constant pressure and in constant volume process, this will highly differ, and that we cannot ignore. So it will absorb different amount of energy if the conditions are different. So you can supply the energy to the gas in constant process, a constant pressure or in constant volume, but in two different conditions it will absorb two different types of heat. As a result, you cannot ignore the condition of constant pressure and condition of constant volume for gases. For solids, for liquid, you can ignore. Now, then we have to define two different specific heat capacity. One is specific heat capacity at constant pressure, another is specific heat capacity at constant volume. Then for gas, I define two specific heat capacity. One is denoted as Cp, another is denoted as Cv. Cv. Okay. Now, heat energy is supplied that is del Q del T at constant pressure for unit mass. One by m, Cp equal to 1 by m del Q del T. But I consider that for unit mass it is defined, or 1 mole. If I define with respect to 1 mole, then it is called molar specific heat capacity. So I consider from beginning that it is 1 mole. So no need to write this one. So just we consider 1 mole. Mass is from the beginning considered as 1. Then this one can be written as del Q del T at constant volume. So amount of heat energy required to increase the temperature of unit mass of a substance by 1 degree Celsius in constant pressure, and here it is in constant volume. If you write in SI system, it will be 1 kg mass and it will be 1 Kelvin rise in temperature. Okay, then how to find this one? Check. dq dt at constant P is there. So Cp can be written as du del U del T at constant pressure plus P del V del T at constant pressure. I substitute dq at that point. Here in presence of that I substitute this one. So first term will become del u by du by dt, but at constant pressure, so I write del u del T at constant P. Second term P is constant, so it will be del V del T at constant P. For Cv, what will happen? du will be there. So first term will be del u del T at constant volume, but next term will be 0 because constant volume means dV will become 0. Constant volume, V constant, so change in volume will become 0, so dV 0, so second term will not be there, only one term. Now which one is greater, Cp or Cv from this? Why? There are two terms and there are one term. No, you cannot argue like that. These two terms are not equal. This is with respect to constant pressure, this is with respect to constant volume, and who can say that taking the constant volume this is greater than this one? If these two terms both are same, this is P, this is also P, then you can argue that there are one more extra term and then this one is greater than Cv. But derivatives are with respect to different constants, so you cannot argue like that. But still Cp is greater. How? I will take one more example. Come. See, suppose I want to give him 1 rupee coin one by one until in his pocket the amount of rupees will become 100. Suppose I am giving him 1 rupee, he put it in the pocket, next put it in the pocket. So how many times I have to give? 100 times. So how much rupee I will give? 100 rupee. In his pocket the amount of rupee will be 100. Now suppose I am giving 1 rupee and after each 5 rupee it took 1 rupee and put it in other pocket. So how much total amount of rupee I have to give? After every 5 I have to give one more, because he is actually doing these things. So 5 multiple of 100, that is 20. So I have to give him now 20 rupees, such that one time will come when in his pocket the total amount of rupee will be 100. That means how much I have to pay? 120, such that in his pocket the amount of rupee will become 100. Now why this occurs? Because he is not storing the rupees in the pocket, he is also doing some bypassing of the rupees in other pocket. Okay. Now think in this case, you are trying to increase the temperature of the gas by 1 degree Celsius. That's why you are supplying heat, and in this case the entire heat energy that you supply, gas utilize it to increase its temperature. That is it. What about these two? Are they equal or not? They are not equal. But in physics everything can happen. When I can consider them equal? Only in case of ideal gas, and we consider ideal gas only, then we can consider them equal. Why? Internal energy. Why internal energy comes? Internal energy means total mechanical energy, that is kinetic energy plus potential energy. What potential energy an ideal gas have? What is the potential energy of an ideal gas? 0. Why? There are no intermolecular force considered between the molecules of an ideal gas. So if there are no intermolecular attraction force, there will be no potential energy. Like you consider in gravitational force, there is attraction, that's why there is a gravitational potential energy. There are spring forces, then that's why there are elastic potential energy. There are electrostatic forces, that's why there are electrostatic potential energy. But for this one, there is no intermolecular force between the gas molecules, so there will be no potential energy. So only energy for the ideal gas, internal energy for the ideal gas, is due to the random movement of the gas molecules, and that is purely kinetic in nature. And you have earlier said that average kinetic energy of the gas molecule is related to its temperature. At the beginning of the kinetic theory, when we are discussing temperature, we are saying that average kinetic energy of the random motion is the temperature. So the internal energy of an ideal gas only depends on its temperature. There is no potential energy dependence, so only depends on its temperature. So it will not depend on its volume and pressure. So whatever you keep constant, whether volume or whether pressure, that does not matter. You are preparing for NEET. Someone is in the president position of Bangladesh, that will not affect you. So like that, U is only dependent on temperature for ideal gas. So whatever we can do with pressure or volume, that does not affect. So that means del U del T only matters for ideal gas. Whether you are keeping P constant or V constant, that does not affect. So both of them are same. So I can say, if I subtract this Cp minus Cv, I will get only this term, del V del T at constant pressure. del V del T at constant pressure. Now we consider 1 mole of an ideal gas, so I can write PV equal to RT for 1 mole. Okay, then pressure is constant by taking, because here what we require, del V del T at constant pressure. So pressure kept constant, calculate the derivative of V with respect to T. It will be then del V del T at constant pressure. This is R, because del T will become 1, derivative of T with respect to T, that is 1. So what is coming, this R, substitute it here, then you can get that relation Cp minus Cv equal to R. Okay. Any question if you have, you can ask. Now, see, now if we consider that temperature of the gas is remain constant, then which one is 0? du will be 0 and dq will be directly used, is totally used to do the mechanical work by the gas. Gas will absorb this dq and completely do mechanical work with this one. This is called the isothermal process. But remember, this one is an ideal case. There is no such gas which will absorb the energy and will not increase its internal energy and utilize entire heat to mechanical work. Similarly, dq0 means adiabatic process, isochoric, isobaric, all these are ideal processes that we will discuss. Now, first one is that can we calculate the work done in adiabatic process? Work done by a gas in adiabatic process, we can calculate. How? Because work done dW, that is written PdV. Then for calculation of the total work done, suppose from state 1 to state 2, that is integral PdV. Now for doing that, I have to write P as a function of V for integration. P as a function of V. Now see, for 1 mole of an ideal gas, PV equal to RT. If you consider n mole, then it will be nRT. I consider just 1 mole first, because if I can derive it from 1 mole, you can already put directly n instead of nr and calculate for n mole. For 1 mole, PV equal to RT. Then I can write P equal to RT by V, and I can substitute it there in place of P and write 1 by 2, 1 to 2 RT equal to dV by V. Now tell me why we can take R and T out of the integral. R is constant, but T, since we are considering isothermal process, isothermal means temperature constant, so in this case T is constant, so I can take T out of the integral as if it's a constant. For all other processes you cannot take T out of the integral, only for isothermal process you can do, because isothermal means temperature constant. Then remaining part of the integral will be W equal to RT log of V, limit is from 1 to 2, 1 to 2 means V1 to V2, so we can write W equal to RT log V2 minus log V1, that is log of V2 by V1. That is the work done by 1 mole of an ideal gas in isothermal process. Okay. Now, for adiabatic process, which law is followed by the gas? In isothermal process, PV equal to constant, because T is here constant in isothermal process. In adiabatic process, PV to the power gamma is constant, where gamma is the ratio of the specific heat capacity. Now, how it is P V to the power gamma, that can also be proved, but we will not do it here because the proof and all these things are not required. You can only remember that P V to the power gamma equal to constant. If you go through your textbook or anything, there is that proof how P V to the power gamma will come. Okay. Now, I am just considering to calculate the work done in adiabatic process. See, the same result of work can be used, that is, this one is the fundamental form for work, and in adiabatic process, rather P V to the power gamma equal to some constant. I consider this constant to be C. Then I can write here that C common integral V to the power minus gamma dV 1 to 2. 1 by V to the power gamma is there, C by V to the power gamma is P. So I write it C into V to the power minus gamma dV. Now its integration will be V to the power minus gamma plus 1 by minus gamma plus 1. Minus gamma plus 1 by minus gamma plus 1. So it will become C V to the power minus gamma plus 1 by minus gamma plus 1. 1 to 2 means state 1 to state 2. Okay. State 1 to state 2. Then W can be written as C by, just check, 1 minus gamma into V by V to the power gamma 1 to 2. I am not skipping any step. C by 1 minus gamma V to the power minus gamma into V, that can be written as V by V to the power gamma 1 to 2. Now I put the limit. It will be C by 1 minus gamma into V2 by V2 to the power gamma minus V1 by V1 to the power gamma. Okay, V2 by V2 to the power gamma minus V1 by V1 to the power gamma. Check. Now I can write this one in this manner: 1 by gamma minus 1 into C V1 by V1 to the power gamma minus C V2 by V2 to the power gamma. Check. I change this one, 1 minus gamma to gamma minus 1, means taking 1 minus common, I add that minus inside. So then it will be, I multiply that minus inside. So it will be C V1 by V1 to the power gamma minus C V2 by V2 to the power gamma. Okay. Then what is the law in adiabatic process? P V to the power gamma equal to constant. Then I can write for two different states. First state P1 V to the power V1 to the power gamma equal to that same constant, and even P2 V2 to the power gamma will be equal to same constant. Then tell me, what is P1? C by V1 to the power gamma. C by V1 to the power gamma. Put it P1. It will become 1 by gamma minus 1 into P1 V1 minus P2 V2 P1 V1 minus P2 V2 because from this I write P1 means C by V1 to the power gamma. There is C by V1 to the power gamma, I put it P1. C by V2 to the power gamma, I put it P2. Now consider the equation of an ideal gas, PV equal to nRT for n mole. Then can I write P1 V1 equal to nRT1, P2 V2 equal to nRT2, because temperature can be changed, because this is an adiabatic process, this is not isothermal. In isothermal temperature is constant. Then P1 V1 and P2 V2 can be replaced by nRT1 minus nRT2. So n and r can be taken common, and you can write the work done in adiabatic process as nr by gamma minus 1 into T1 minus T2. This is the final result. If you remember, then you can also write this R by gamma minus 1 as CV, specific heat capacity at constant volume. CV, R by gamma minus 1. There is one proof in your mock paper, one question in your mock paper. For a particular gas, you have to calculate CV, and it is coming R by gamma minus 1. So you can also write this expression as NCV into T2 minus T1. This is the work done in adiabatic process. Now, I will ask you one question. In adiabatic process, this is the work done. Now for doing work, what is given to the gas? Heat energy, because first law starts with that dq equal to du plus pdv. Then when you are supplying heat energy, a part of energy is utilized in internal energy, increase in internal energy, and remaining part is utilized for work done. Now in adiabatic process, how much energy you are giving, heat energy you are giving to the gas? Nothing. Means adiabatic process means dq equal to 0. Then how the gas will do work? dq equal to du plus pdv means once you give heat energy to the gas, a part of heat energy gas will utilize for increase in temperature, another is utilized for for doing mechanical work. Now you are not giving any heat energy, dq equal to 0 in adiabatic process. Then how the gas will do work? We have calculated that work is there. You cannot say work is 0, because in that case, if work should be 0, then T1 equal to T2, which will lead to the isothermal process. So T1 and T2 are not equal. So gas will definitely do work, but how? You are not giving any heat energy, then how gas will do work? Suppose all of your parents supply you some money, and here SCST is allowing you to go to the Shillong for any party or any program that you can visit Shillong. You can travel to Shillong, roam here and there. Okay, for outing you can go. Okay. Now, suppose you are coming here with a certain amount of money, and every month your parent is sending some amount of money to you. Then in the weekend you are allowed to go to the Shillong for party and doing things. So you are spending the money there for amusement and all these things. This is the mechanical work that you are doing. Okay, and how you can do this mechanical work? Because there is a constant supply of money from your parents. Okay, initially some money is given to you, but after that in every month there is a flow of money from your parents. Now think of it, this supply line is cut and your parent is saying no. Okay, the SCST may allow you to go to the Shillong, but we will not supply you money in every month. First, what you will do? First you will show some anger or agitation on parent. Okay, then you will do, okay, I have sufficient amount of money in my pocket and I will do amusement with this money. So you are going to Shillong and every money is spent, everything. So suppose 3 to 4 weeks you can do all this party, and what will happen after that? There is no flow, chain cut. What happens? You have no money in the pocket. Suppose your friend has still money in the pocket. He is saying that okay, I will go. You will say, I will know. I don't like this amusement and party. Okay, let me stay here. I will focus on my study. Means your internal energy is actually, you spent your internal energy to do the amusement. Means gas will spend its internal energy to do the mechanical work if external heat is not supplied to the gas. As a result, the internal energy of the gas, like the money in your pocket, will decrease. So you are cooling down, gas will also cool down. So adiabatic work done always represents cooling. There is a very common example that adiabatic work done is cooling. See, open your mouth and put your hand in front of it and do, giving some air to this, blow some air on the hand. It feels hot air, na? Okay. Now, hot air means when you are opening your mouth this much large, heat energy is coming. Now, blow the air like this, you will feel that it is cold air. Means this much opening is there. So heat energy coming is very low, almost zero. So gas is running through that small portion. And now after your mouth, gas is expanded. So it is doing mechanical work. So how he can do mechanical work? By spending his internal energy only. That's why it is cold air. Because adiabatic work done represents decrease in internal energy. That's why you feel that whenever you are blowing air like this, it will be cold. If you are doing like this, it will be a hot air. Gas will not cool because you are supplying energy. Now since you releasing the air through this small hole, the heat energy cannot come with the gas. Now as a result, gas is coming through this small hole. Initially its volume is small, but since it is going outside, it can expand in the free air. So expand means it is doing mechanical work. But how he can do mechanical work? Heat energy is not supplied, so he will utilize its own internal energy to do this expansion. That is mechanical work. So internal energy drops means temperature drops. That's why you are feeling cold. Another thing is there. How many of you run bicycle? Bicycle, if the bicycle tire leaks, the leak portion through which the gas is coming out, it is colder. Because the same thing, it is coming through pinhole, expanding, and due to expansion, it is doing mechanical work. How he can do mechanical work? At the expense of its own internal energy. So the temperature drops. So adiabatic process always gives us cooling. The equation will also say gas is doing work means W is positive, but then for W to be positive, T1 should be greater than T2, then only W is positive, because gamma is always greater than 1. So for W to be positive means gas is doing mechanical work, T1 should be greater than T2. What is T1? Initial temperature. T2 final temperature. So initial temperature what? Final temperature lower than that means there is a cooling. So adiabatic work done always represents cooling. Okay. In volume. And what is the work done in isochoric process? Nothing. Volume is not changing, so how can it will do work? Its work done in isochoric process is 0. So only 3 process there is work done in isothermal, in adiabatic and isobaric. Isochoric, no work done. So this much we will do today, because the other topic cannot be completed in 5 minutes. No topic can be completed. So the graph portion is there. For graph calculation of the work done, internal energy, heat absorbed, that we will discuss little bit. Some question we will practice, because that will come directly in the exam, and little bit of the second law of thermodynamics we will discuss, because second law is another important law where from heat engine many question will come regarding its efficiency, heat engines, other processes, all these things, and some basic knowledge of entropy.